Hello maths fans! Today I'm bringing you a very special video which is going to be a live recording of one of my tutorials here at Oxford. We are joined by two of my second year students. This is Will and Luke, and we are going to be going through a past exam paper from the second year course in metric spaces and complex analysis, because these poor souls have exams in a few weeks. The plan here is to basically record everything, so we have a couple of cameras set up in the room. We are going to, from this point onwards, completely ignore all of the cameras, and the idea is to give you watching this at home a little bit of an insight into what a real Oxford University mathematics tutorial actually looks at. So, we hope you enjoy it.
How did you come up with your one, Luke, for the counterexample, the first one?
I think sort of thought about something which is never going to have an equal point, something simple, and sort of, I think I got x plus 1 over x.
Cool.
Yeah, that sort of makes sense.
Because if it had a fixed point, right, so if we consider f of x is 1 over x plus 1 over x, what would be true if it had a fixed point?
Then,
If fixed point exists. Oh, right, you'd have 1 over x is 0.
yeah.
Which,
Which can't happen.
right, yeah, because that has to equal x.
Yeah.
If this point exists, then then we know that f of x is equal to x, so here, i.e., 1 over x equals, tends to 0.
Yeah.
Which is a good one.
Yes, because you can't have, there's no point in infinity or anything, so
Yes.
yeah, that's fine.
Yeah, so I think once you I'm just trying to remember exactly when I did this question, but that was kind of my thing. I was like, okay, well, suppose there is a fixed point. What has to be true? And as soon as you write down that equation in algebra,
Yeah.
I don't know, it kind of...
So just to check, your space X that you chose for this, because obviously you can't have 0 inside of your space because you can't have 1 over x there.
Yes. So you just need to be a little bit away from 0. I think I just did 1 to infinity.
Okay,
As an interval.
That works.
Did you just...
I missed that over there. Should have been...
Yes, you probably should say that you're... So I just had the metric space x is equal to 1. That's a terrible square bracket. 1 infinity.
Cool.
Which is complete.
Yeah.
Because...
subset of complete metric space.
Yes. Good. It is complete, yeah. I had to think on it for a second. Yeah. So then that just works basically. But I think anything as long as you don't start at 0.
Yeah.
Right? It can be any epsilon.
Yeah,
infinity.
cool.
Just avoid 0 like you say, because then the function's well defined. And then it's all okay. And our metric, I don't know if we had to define the metric, but you would just take modulus.
Yeah.
Standard one is just the straightforward way to do it. Good, right, so that was 3 marks.
Yeah.
And you got 5 marks for part 2. And this one, true or false?
I reckon it's true.
I mean, there's a big clue in the fact that they're identical statements, and one of them is complete and one of them is compact, right? So again, exam technique, when it's prove or disprove the following, probably, not always, probably one of them is true and one of them isn't. Right? So if you've already found a counterexample for the first one, then this one's probably going to be true.
So, I mean, I didn't get time to try this, but compact is complete and totally bounded. So I was thinking, well, maybe you could use the totally bounded option, because the example we chose here is kind of interval 1 to infinity. That's not totally bounded. So maybe if you had a totally bounded space, you could kind of strengthen this condition and say this was less than k times distance between x minus y for some k less than 1. But I wasn't. Maybe that's not the way to do it.
Well, I mean, that is the key thing that's going to get you that it's true.
Yeah.
Right, as you say, but this is what I was saying in the first question about we had the compact set mapped into a compact set and it was continuous.
Yeah.
It means it attains its bounds. So you can argue through a similar way, and I think that was sort of what you did as well, right? Did you?
I did a distance from x to x. But now you have to continue to attain its bounds.
Yes.
Then, it was 2 weeks ago, so I can't remember what from there, but...
I'll write out the key steps I put down here then. So I just said, right, so we're going to try and prove this one. So what have we got to prove? If we have a compact, x d is compact, compact metric space, and f is continuous. Okay, f x to x is continuous, and we're told d of fx comma fy is less than d of xy. So it's a contraction. Then f has a unique fixed point. Okay. Interesting. I missed the uniqueness bit. Oops. Anyway, right. So I defined phi of x to be the distance between f of x and x. Then we know that x is compact, so phi attains its bounds. So phi attains bounds because it's mapping from x to x to complex sets. So call the minimum at x hat. So we can say the distance between f of x hat and x hat equals epsilon.
Yeah.
Right. But now, what happens if we apply f again, basically?
So you'll have...
You'd get that there was the distance between f of x and f of x hat was less than that because it's a contraction.
So that's equal to epsilon, which is therefore greater than. So like these are the 2 points, right? So this is your x and this is your y.
Yeah.
Which is then bigger than applying f to them again, which is d of f squared. Let's write it as of x hat and f of x hat. But x hat is the fixed point.
Yeah.
Which is, so I know, unless it's the fixed point, because then we can argue, well, that's just greater than or equal to epsilon again. So you've got epsilon is strictly bigger than epsilon, which obviously nonsense.
Yeah.
So that tells you that x hat has to, this in fact has to be 0.
Got it. Yeah.
So the minimum basically must be 0, right? So I guess here we were assuming there was a minimum epsilon.
Yeah.
And you're saying, which is strictly positive, but then if it is strictly positive, then you just apply the apply f again, and then use the fact that d of f between 2 points is less than d of the other 2 points. So you like kind of contract again, and then you're like, but that's also bigger than epsilon. And that's a contradiction.
Yeah. Okay, got it. That's cool.
Yeah. Contradiction. So therefore what it means is that, in fact, the minimum, this cannot be positive, right? It must be 0. So obviously the distance between those 2 points is 0. That tells you that f of x hat is x hat, which is your fixed point.
Yeah. That's really like.
I think we did this on a problem sheet, or at least I remember using this almost exact same proof on a problem sheet question. It might have been a slightly different question, but I remember this idea.
Okay.
For contraction maps. It can be very helpful with contraction maps in here. We'll just apply them again.
Yeah.
And again. And try and get. Yeah.
Well, that's like part of the proof of the actual.
You apply it like n times or whatever, don't you?
Yeah,
exactly. Exactly.
So I guess
It guides you a little bit.
the motivation is like, okay, well, I want to look at the distance between y regular, x, and what happens if I apply. So, and the point of this phi is that you have this minimum, so that if you apply it again, you're going to get a contradiction. Fine. Okay.
Yes. All right, and then we were happy with the end of 2, weren't we? In the end, yeah,
that
we
was
talked
good.
about it as well.
Yeah.
Okay. 3. So, actual complex analysis stuff. You both had some issues with doing the actual Cauchy-Riemann.
Yes, I know. It's one of these things. It's like,
Oh no, you got there in the end, right? I think did you cross out the first page?
I crossed out, doing the
Yes,
verifying
but then you
thing.
eventually
Then I
figured it
got
out, right?
yeah, I didn't think this was helpful.
It's just kind of, I think I just kind of differentiated implicitly, was how I thought about it. So what have we got? We've got, so obviously the first part is like super book work, right?
Yeah.
You get 6 marks for that first part,
Yeah.
defining it and say improve them. And then you get 3 marks for the last bit, which I guess is just meant to be a really neat application of what you've written down.
Yeah.
So if, what have I said? So u squared minus v squared equals x. So if we do d by dx, partial of the whole thing,
Yeah.
then the right hand side is 1. So 1 equals, now what's going to happen if I d by dx?
Oh, so you get 2u and then u partial x.
Yep.
And then minus 2v v partial x.
Great. And then if I do d by dy,
So if you do d by dy, you'll get 0 is equal to 2u u partial y minus 2v v partial y.
That's 2v. Right, so that was the first equation. Right, so now let's do the second one. Same idea. 2uv equals y.
Here we go. So if you d by dx, you'll get 2u partial x v plus 2u v partial x is 0.
Yes, good.
And if you do d by dy, you get same thing with the partial y's is
Yes.
equal to 1.
V plus 2u vy is equal to 1. Right, so now you've got 4 equations in your 4 unknowns, ux, vx, uy, vy.
Yeah.
Solve simultaneously. You did a matrix inversion. However you want to do it, you're just going to solve 4 equations, 4 unknowns. And you will get ux is vy is u over 2u squared plus v squared. There's maybe, looking at that now, possibly was helpful to multiply through by u or v, maybe what I did in my actual working. Which I
That
didn't
would
write
help
out
because
here.
of the y, yeah.
Possibly, I think, is maybe what's happening. Yeah, and then the other one is uy is minus vx. They just come out to be the same as v over the same thing.
This looks familiar now that you write it down. Now that you've written the answer, it seems right.
I think it's just one of those annoying ones,
Yeah.
right? That
I think because I started off doing this, but I gave up too early.
yes.
It's like,
and then-
okay, well now let's try and explain.
yeah, once you start doing square roots and x's and y's, it's not going to go well. Yeah.
So, can I see how you did it with the matrix?
Yeah, of course, yeah. So just sort of crossed out, but you basically do it in full matrix form. You get like 2 individual matrices, and I just solved them both.
This is nice as well. Yeah.
You could probably do some like sort of symmetry arguments and have to calculate them.
Yeah.
I think I just work it out.
That's cool as well. Yeah. That's good.
Right, and then we do multifunctions, logs.
Yeah.
So I actually quite liked this question. Okay, find the holomorphic branch of log such that L1 is 0, blah, 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 right. And then compute I to the I. So you both spotted the key thing, right? Is it in the first quadrant or does it go into the second quadrant?
Yeah. And the value changes.
Yes.
Depending on what you pick.
Exactly. Yeah. Depending on where that cut is.
Yeah.
I think in the mark scheme it said that, because I don't think when the question was originally written, the examiner realised that there was that 2 options.
Yeah.
So I think in the mark scheme it literally said like if you've calculated one of them correctly, then you're fine.
Yeah.
Okay, and then now we've got z squared minus 1. Okay, so how do we split up log of z squared minus 1?
So log of z minus 1 plus log of z plus 1.
Yeah, so 3b. Okay, so log of z squared minus 1 is going to be log of z minus 1 plus, isn't it, log of the other one. Yeah, from properties of logs. And then what do we do for each of the logs?
I don't know how you guys did it. I was thinking like, what I wanted to do was, if I'm looking at log of z minus 1, I wanted to choose my, because this is all about multifunctions, I wanted to choose my argument multifunction so that it would work for anywhere kind of except this branch.
Yeah, exactly.
And then for the z plus 1, obviously the opposite side.
Yeah, no, exactly that. So, because it's telling you what, where we need it, right? So basically, what I would do here is I would look at the domain given, where
Yeah.
the function needs to be defined, and it's telling you exactly where your two branch cuts need to be.
Yeah.
So I would then draw the picture and then be like, right, so for z minus 1, then I'm going from the point plus 1. So that function, if I do it in orange, is defined, so this one is defined from here.
Yeah.
Right, so this would be R1 and this would be theta 1.
Yeah. Cool.
And then it tells you immediately, okay, so I'll cut out that bit. And then
Yeah.
we're good. And then for the other one, you're doing the exact same thing now. This one's at minus 1 over here. So again, you want this to be theta 2 and that distance to be R2.
Yeah.
So this is telling you now. So this one's going to be between pi and minus pi,
Yeah.
and this one's going to be between 0 and 2 pi.
Yeah. Cool. Awesome.
Yeah. So I find these pictures really, really helpful.
Yeah.
Um,
I feel
Those
like
are defining things.
with the exam pressure, it's like very easy to get your pi's and your zeros and your 2 pi's
Yeah.
mixed up. So it's like you've got to write it down somehow.
Yeah, so how did you actually...
So yes, I
write it
have this.
specifically?
So this is my multifunction, that g of zb. So I wrote this down kind of log of z minus 1 plus the
Okay,
argument
yeah.
where this is between 0 and 2 pi, and then log of
And that one is that, okay.
minus pi. So
Because I think the way I would always write these is just say define z minus 1 to be r1 ei theta 1 for theta 1, as we just said, between 0 and 2 pi,
yeah,
and then z plus 1 to be r2 ei theta 2, where theta 2 is between minus pi. So if you sort of write it like this, then it just everything else like immediately follows.
yeah,
Once you define log in the usual way. Minus pi, theta 2, pi. Right. Fabulous. And then what it said something
show that the branch is single valued as we
across the real axis. So what did I say? I just said both of them are continuous.
Yeah,
It's a weird question, isn't it?
I was a bit confused because I mean I've defined the functions. You know, they're the arguments that I chose are singular valued, so it's like it should be fine. The one that causes more trouble is in part 3.
Yes. Yes. You actually have to think about part. Yeah, that one's a
Yeah.
little bit because they cancel each other out.
Yeah.
Is what happens in the next part. Yeah. So I think that's the only reason it mentioned that there, because in the second part, I feel like it's trying to give you a clue for what to do in the next part,
Yeah.
but actually ends up like confusing people rather
Yeah.
than giving you the clue that it was originally meant to be.
Of course, it's single valued. Yeah.
So yeah, so there's not really anything to say except both theta 1 and theta 2 are continuous across that line.
Yeah.
Therefore, the function is nice.
That's cool. Yeah.
That's what you had to say. So when the following sequence of functions converges to a holomorphic f on C complement Z.
Yeah.
So first of all, why are we considering C complement Z?
Well, these denominators vanish when you're on the integers, so there's no way you can define fn.
Yeah, it's going to blow up.
Yeah.
Right, as soon as we have the points, as soon as we get any Z as any integer. And I think you actually did argue this correctly, and you kind of knew what was going on. It is going to converge because it's like a 1 over n squared.
Yeah.
Right, so you're like, oh, it feels like it's going to converge to something, but
Yeah.
as long as I avoid those things, we're okay. What specific convergence test or convergence theorem would you be applying to something of this form?
I've written it here already. Oops. Yeah, it's uniform convergence on compacts or local uniform convergence.
By
M-test.
M-test. So we mentioned this one the other day, didn't we? Right, by M-test. So you can argue uniform convergence by M-test, basically. So you just you have a point, right, so you kind of got your complex plane, but you've got all these dots where all your integer points are.
Yeah.
And you're like, okay, so if I'm a point away from that, I can get an epsilon ball around it, as long as the radius doesn't extend to, it's going to be definitely less than 1.
Yeah.
Just to not to hit
This
it.
is the diagram that
Yes,
I drew. Yeah.
something like yeah. Right, you can definitely do it. It's going to work, and the M-test is going to tell you it's less than a 1 over a z squared type thing, which is going to converge. So uniform convergence by the M-test. Right. There's only 2 marks for that, so I don't think they're expecting like a full proof.
There were only 2 marks for showing that this converges to
A holomorphic function. Yeah.
Really?
Literally. Yeah.
I did a page for this.
Yep.
Rubbish.
Yes. Given the fact, I don't think if you read the examiner's report, I don't think anyone got the closed form expression for f. So you may, in theory, the examiner may have been like awarding more marks for the first part.
Okay, yeah.
You know, to kind of try and offset the fact that people, you know, for those who had made a good bit of progress through the question.
Yeah, yeah.
It feels like it would have been a fair thing to do.
No, that's good.
Okay, so what properties do the Fn have? Start with that. In terms of trying to get this closed form expression. So let's think about what properties do the Fn have?
Well, I guess this is Eve. I think even. Maybe I should be saying that. I don't know. Yeah, I think it should be even, right? Or maybe not. No, maybe that's wrong.
I think it ends up being odd.
Oh,
Actually.
oh yes, because of the minus 1 over k. Yeah.
Yeah. I mean, there's a big clue because it says explain why fz is periodic.
Yeah. Okay.
Because what happens if you start at z and then you go to z plus something, it will be z plus blank and it's the same. What would the blank be?
Yeah. So.
Z plus n for any n because it's symmetric, it goes to minus infinity and infinity.
Mm-hmm.
At any integer, it's going to be the same basically.
But you have to be slightly careful because of the power at the top.
Of course, yeah.
Yeah. So
Yes.
minus.
So z to z plus 2
Yeah.
would be the smallest such integer.
Okay.
You can't just add 1 because then it will flip from a plus to a minus on the top.
Yeah.
For each matching term by term. You know, if you think of, I'm thinking about Fn here rather than yeah, so I think it's easier maybe to think of the properties when it's finite. But yeah, you're right. So it's that shifting by an integer and like the smallest, you know, because it's like cos and sine are 2 pi periodic, but you could also argue they're 12 pi periodic.
Yeah.
Right, you kind of want the smallest bit.
Yeah.
So there's a clue there when it says why fz must be periodic.
Fine.
So you're arguing that the Fn's are, so therefore in the limiting case you would also expect their limit to be periodic.
Yeah.
So z goes to z plus 2, and that's going to be helpful because the only real periodic functions we ever study.
Yeah. Yeah.
Sine and cosine.
Yeah.
So it's telling you, so instead of being 2 pi periodic, if it's 2 periodic, what like form does it have to have? Can't just be sine of z,
Sine pi z.
sine pi z,
Yeah.
or cos pi z.
Yeah.
Right, so immediately this is telling you it's going to be something like, right, sine of pi z or cos of pi z. Just a helpful thing to think about.
Yeah.
Again, it's not in any way a proof, but they're the kind of simplest possible things you might try.
Yeah.
Okay. Now, in terms of the Fn's, thinking about poles, let's talk about holomorphic.
Yeah.
What poles does it have?
Double poles.
Right. So we have double poles at each integer. So rather than being double poles, if we integrate. We integrate this. So if we integrate, then we're going to get single poles. Right, because obviously, so being to the power minus 2, it becomes the power minus 1.
Yeah.
So you're going to get simple poles, which has residue. You also get a minus 1 factor on top, with residue still minus 1 to the k. So we can say that f of z is therefore equal to minus g prime of z, where g prime of z has the simple poles residue minus 1 to the k.
So just to be clear, like, are we integrating f?
The limiting function is just minus infinity to infinity of
Yes.
this.
Okay, cool.
Yes. Yeah. So f of z is from k minus infinity to infinity minus 1 to the k over z plus k squared. Right, so let's integrate. So we're arguing that the integral of f of z then now looks like the sum from minus infinity to infinity Right, so we've got the thing to the minus 2, so we increase the power by 1, minus 1, so it's going to be a minus 1 to the k over z plus k squared. Sorry, over z plus k.
Yeah, and this converges uniformly. This converges uniformly, so you can swap limits in integration.
Yep, yeah. So, yes, so I was in that, right. Yes,
Yeah.
since converges uniformly, yeah, good point. Because I've just, so that allows us to integrate term by term.
Yeah.
Yep, since converges uniformly. Okay, so I don't think you actually need the residues of the double pole, and it might be the case that I've written that and I was wrong, because you don't need it.
Okay, cool.
So I literally could be wrong about that, which is maybe why we're struggling to prove it. Because the key thing is you integrate this, and now you can say, this is something we recognize. This is the idea, to say, this we recognize. This we recognize. Because the residues now are very clearly minus 1 to the k. So minus 1 to the k.
Oh, yeah.
So
Oh, yes, because,
residues now, because it's just a minus 1 power.
Yeah.
Residues are now minus 1 to the k. So that's all good.
And all of the other terms are like holomorphic at k, so they all...
Take the limit. That's
That's
fine,
yeah.
right? Because, yes. Okay, so what we actually want to do is if we do minus that, now the residues are correct.
Yeah.
So minus that integral gives us this thing. The residues are minus 1 to the k. The poles are all simple poles at the integers. And because our original function was 2 periodic, this will still be 2 periodic.
Yeah.
And 2 periodic. So given this information, you are then meant to deduce that minus the integral of f is therefore equal to pi divided by sine of pi z. Because, of course, the zeros of sine of pi z, simple zeros at all of the integers. And why did I put the pi on top? Because, yes, the pi is on top, because now when you differentiate this and if you were to calculate the actual residues, if given this function and you try to calculate the residues, I think you need the pi on top, otherwise you get minus 1 to the k times pi, because of the pi factor when you differentiated the sign.
Yeah.
Using like a L'Hopital rule type thing.
I get that this works as you can check that it gives the right
Has all of these
periodicity.
properties. Yes.
How do you know? I'm sorry about this question. How do you know this is the function?
I thought of it as we've got enough information here that tells us what the function has to be, but I'm not entirely sure if whether we need additional. Right, it's one of those where it's almost like, I feel like it's almost like solving a crime. You've got the evidence of it. You know the residues.
Yeah.
You know there are simple poles. You know it's 2 periodic.
Yeah.
There's a very limited number of functions you could write down with that property.
Yeah.
Whether or not it's specifically unique, I don't know. Off the top of my head, I honestly don't know.
Yeah.
But I feel like, as you say, we only need one.
Yeah.
Because couldn't you add a sine pi z to that and it would still satisfy everything?
You possibly could, but then would it not maybe add in other residues? Would it not slightly alter the residues?
Don't think so, because or would it? No, sine pi z is holomorphic everywhere, so it wouldn't affect C minus.
Oh, sorry. So yeah, if you had this function plus something holomorphic.
Oh yeah.
My bad.
Yeah.
Yes, then of course.
Yeah.
So it is non-unique. Okay, good. Thank you. Yeah, because you could add anything holomorphic, and none of this. But this is telling you what the bad behavior is, right? The bits where there are problems. That's what it's telling us.
Cool.
So we need something like this, and then of course the point is now minus and differentiate it to get what f actually is.
Yeah, fine.
Which is when you do that, it's pretty awful. F is pi squared divided by sine of pi z times tan of pi z. So how on earth are you meant to get that? I'll be honest, I don't remember the exact word in the examiner's report, but I'm pretty sure nobody got the function.
Yeah, okay. It's...
And that's not even the question. That was actually the last part of the question. Was that you need to do this. Because you've now got to actually do the expansion around 0.
Yeah.
Because that's... Hopefully you can see that this is clearly an expansion around z equals 0.
Yeah.
Is what's telling you this is going to give you the answer. So you do the expansion around z equals 0, and then that gives you the sum of all the residues.
Cool.
It's pretty horrible. I think the key, because we already spent ages on this question, the key takeaway is, and I don't think you'd be tested on this, but is this kind of concept of given certain residues and given certain poles, can you write down a function that's going to have those properties? And it's only going to be something like this. I don't think it would be this hard, to be honest. But like, you know, so if you were told there's because for some of them it's obvious. If you're like, the function has a simple pole at 3 and the residue is 1, then you're like, okay, so the function is 1 divided by z minus 3.
Fine.
It sounds silly when I make it that obvious, but it's that kind of, that's what the question's testing. Can you go backwards? Rather than starting from, here's a function, work out its residues and its poles. If we tell you the residues and poles, can you write down the function?
I guess.
I think that's what it was trying to test. But just not, like, the question's too hard. It really is. Okay, number 4. So, classify with brief explanation singularities of the following functions after we've written down Lorentz theorem. So everything you've said is correct here. However, you were meant to relate the singularity to what you get in Lorentz.
Okay. Yeah. So removal singularity, you get Taylor's. Taylor expansion. If you get polar order K, then you get it's a finite principal part. So you go up to the z c to the minus k, which is like and if you've got an essential singularity, then your principal part is infinite many terms.
Yes. Yeah. Exactly. Good. And then I think maybe you missed this question, Luke, but it does say at the bottom bit, for g of z, compute the residue at every pole.
Oh yeah, I must have missed it.
So yes, you were just meant to calculate the residues. It's a little bit of a pain, but I think L'Hopital's rule is the easiest way to do it, actually. Is that how did you do it?
If you can write your function as like g of z over h of z, this is holomorphic.
Where g is not 0 at the a. Yes, exactly.
So this is not 0, but
yes,
0
over h prime. Exactly. Yeah. So no, exactly that. So basically, it's just residues are just equal to exactly what you've written, which is just going to be 1 over the derivative d by dz of 1 minus z to the n, evaluated at z equals omega n, where omega n is e to the 2 pi I, omega k, that's actually right as, e to the 2 pi I k over n, yes. Right, there you reach the unity.
That's okay.
So you just differentiate the bottom, so you're just going to get minus n, because it is just 1 minus z to the power n, isn't it? Yes!
Yeah.
So you're literally just going to get minus n times the thing. So thing on top. Yeah, so so therefore, so residue is literally just minus omega k over n. Yeah. And I think especially the way that it's thrown in at the end of the question there, you don't have to justify any of like why this is true. Yeah. It's just compute it.
Just do it.
It's like literally just for 2 or 3 marks. Okay, and then the last one now. So this is what are we doing on this one? So we've got a z equals 0 pole, haven't we? And it's going to be order 3.
Yeah.
And you have to go through and do the expansion.
Yeah.
Which is a nightmare. Well, no, that one's actually not that bad. The others are nightmares. You get minus a third for that, which I think I remember you both got.
Yes.
Which is good. Yeah. Now, for the other ones, the other zeros of the hyperbolic sine function, right? You've got double poles at z equals n pi I.
Yeah.
So then how did we work out those residues?
So...
Because you didn't quite get this one, did you?
No.
Right, okay. But you did get it to work, right? Yeah.
I got this, so...
You did get the same answer as me.
What I wanted to do was write like a shine or cinch or shine.
I say shine.
Shine.
I say shine.
Right. I'll see if I can say it correctly. See if I write shine in terms of sine, and then I know what the roots of shine are because I know what the roots of sine are. So
Okay.
I make
yeah.
sure that I've got all of the roots, or all of the residues.
Yeah.
Sine z is roots at pi n, so shine is roots at pi n I, so that's all fine. And then it's the same thing with, for me, I always do the substitution kind of z minus n pi I, so I'm always expanding around 0.
That's what I did. Z minus n pi I.
Yeah. But it turns out that the shine squared of your substitution is the same as shine of z anyway.
Yes.
That's convenient.
Did you get that?
So I
Yes.
did that substitution, did that there, so I got 1 over z, nu z plus n by I, 1 over sine nu z squared. Is there then?
Because we don't have that factor there. So if you compute, so if you just literally use double angle formula, right? Sorry, addition formula.
Yeah.
So if you compute shine of z minus n pi I, right? So that's definitely what you want to do. And then obviously you rewrite it in terms of cosh and shine, but it turns into, when you square it, so this one from the double angle formula is minus 1 to the n shine of z. And then when you square it, therefore, they're the same.
Yeah.
So shine squared of z minus n pi I is just shine squared of z. Right, so that's from double angle formula for hyperbolic functions. So it's a little bit annoying, you need to remember that, but anyway.
So you can
Or
just
turn it
write
into
it in
sine, like you
sine.
said.
Yes.
Yes. So all you actually have to do is substitute, you just replace that by that in the formula.
Yeah.
Because so then it just becomes that. Okay, so then f of z is then just 1 over z shine squared of z minus n pi I, right? Okay. And then I've done minus n pi I plus n pi I, just so that one's in the same form. Because I'm going to Taylor expand that, like so. And then I've got that one. Oh god, and then I'm going to pull out an n pi I, get some other bits, and then I've got that. And then I have to keep going because you're trying to get your c minus 1 coefficient, and then it eventually comes out to be 1 over that thing squared. So it looks like you've maybe just not pulled out a second factor that should have come out, and then it all kind of behaves okay.
Possibly, yeah.
Because you've got like one of the factors.
Yeah.
I don't know if there's much use in us going through all of the expansion.
No, yeah.
Because it's like, it's just doing lots of horrible Taylor and binomial expansions.
Yeah.
But it does look like maybe that's what's happened. So do you then pull that factor out? So it's here, isn't it? Something, why have you just got one of them there? It's because you can't expand this because you've got a z plus something. Okay, so this should be, you're doing an expansion here in shine.
Yeah.
But this should be, instead of being a z, this should be z minus this.
Okay.
Here.
Yeah.
So then if it is, now you've got 1 over thing plus thing cubed.
Yeah.
So you pull out the thing.
Yeah.
And then that's going to give you 2 lots of,
Oh yeah, I see.
right, of that there. Because you always want to get it so that it's 1 plus something, and then you do your binomial.
Yeah.
That's the key thing with all of these calculations, actually.
Yeah.
It always comes down to that. If you ever forget to do that and try and do a binomial, it won't work.
Yeah.
Like the coefficient you want also basically always comes out from making this a 1.
Yeah.
I see. Yeah.
That's like the key thing to all of these questions. Okay, so then, yes, so that should square, and then
I think
it works.
like a nice way of, especially when you've got different points going on, is like, because you've got to do 1 over z shine squared of z. So if you just do the expansion for shine squared of z, or 1 over shine squared of z, and then you just do your expansion for 1 over z at whatever point, and then you can just multiply the series together to get your final series. So you can kind of handle them separately, and maybe it's easier to do kind of one at a time and then multiply them at the end.
Mhm.
I see. Yeah.
It's probably what I should have done.
All right, counter integral. So you didn't spend much time on these ones, did you?
Didn't know. No.
but I guess we can just go over the key steps maybe rather than the whole thing. Because obviously Will did, but there's only a few things to mention here. So, right, Cauchy-Riemann integral formula, prove Liouville's theorem. They don't tell you it's called Liouville's theorem, but that's what it is.
Yeah. I did this question just using what we found in part B.
Yeah.
And I was trying to do the same thing for this integral, but
I think that's what you got.
I was getting really stuck.
that's what you
And I
got
was like, oh well, if it's integral your residue theorem, then you can just do the. But yeah, cool.
No, you can definitely use the residue theorem.
Okay, cool. I'm just going to use the residue theorem next time.
Yes. Yeah, because what would f of z be for part 2? Because this is the one that you seem to struggle with what your f of z was going to be. So if this is just a standard contour integral question, do this using the contour integral.
Yeah. So for this one, it kind of I guess what you have is that you have.
So you got 4 poles.
Yes, but 2 of them would be inside my semicircle and 2 of them would be outside.
Yeah, exactly.
So I only need to consider these ones, and I can use the semicircular contour, and I can. Would I be able to say that this disappears?
Yes.
Yeah.
You can. Yeah. Upper half plane, semicircular contour. You can do lower half as the same thing.
Yeah.
Because these 2 are outside, so it's all fine. The arc does disappear.
Yeah.
When you let R go to infinity. And what's f of z?
Oh, it would just be your z squared over 1 plus z
Yeah,
over 4.
that's it. Yeah, that's
So
all you were
much-
meant
so
to do.
much easier,
Yeah,
yeah.
that's all you were meant to do. Yes, that's all you had to do.
If you did your lower semicircle, your winding number would be the opposite. So you have to.
Yes.
But it's
Would it make
fine.
any? I don't think it would make any actual difference though.
No, yeah. You just.
Because you'd be going the other way along your integral,
Yeah. Yeah, fine.
so they'd sort of cancel out in that sense, right? Because you always keep the region on your left.
Yeah.
Classic.
Oh, I'm so kicking myself now. I should have just done that. It's fine.
Yes. So that's all there is to it. This one you want to do, so it's similar to what we were just talking about.
Yeah.
You want to just differentiate the bottom term.
Yeah.
Because it's something, a holomorphic function on the top over other functions, so you evaluate at the point,
Yeah.
calculate your residues, yes, and then it turns into, what did you get? Got whatever the residues were. Yes, you have to. I eventually had to substitute in there for what those roots were. These 2 things to get pi over 2 root 2 at the end. Why do you have to be careful about this one? We've seen a similar question on one of the problem sheets. When you're picking your contour.
Well, I guess if you to do it with residue theorem, you have this. I mean, you've got this x squared term here, but as this cos px kind of as x approaches 0, cos px approaches 1. So if you wanted to do residue theorem, you would have to do something like so you would use symmetry to argue that you could replace this with logarithm infinity. And then you would, because this is a simple pole, you can do your indentation.
Yeah. Yes. Yeah. Which is maybe why you thought you had to use this one, because that was an indentation argument for that part.
Yeah. Oh, yes, it was. Yeah.
Possibly it was him. Yeah. Maybe why you're thinking that. Yes, but the thing you have to be careful of though is you're going to do this. You turn the cos into e to the I pz.
Yeah.
Right, plus e to the I minus pz. And you want to argue via Jordan's lemma, so you can use the upper semicircular one for positive p and the lower semicircular one for negative p. So your final answer is actually mod p times pi over 2, because it depends on whether p is positive or negative, which we're not told in the question, which is a bit cheeky.
I just assumed that p was positive because you can replace cos px with minus cos px. Sorry, cos of
Yeah,
minus
that
px,
is also true, yes.
And it'll be fine.
I suppose it depends on how much the examiner is allowing you to kind of generalise versus doing specific cases.
Yeah.
Maybe. But did you look at part B at all, Luke?
I didn't know. No,
Okay.
kind of a bit short of time because of the
I mean, just because it's just worth mentioning because it's an important concept. So the idea is just you have this point x prime, which is a problem point. So
Yeah.
you're just doing, it's basically just an indentation contour
Okay, yeah,
is what it's asking. So you have your indentation contour at some point x prime. So what residue do we get there from this point x prime? We don't get a full, sorry, you calculate the residue, but the residue theorem, you don't get the full residue anymore.
You get pi I times the residue.
Yes, but with a negative.
Negative, yeah. 'cause
Minus
it's,
pi I
clockwise, yeah,
times the residue at x prime. Yes. So it's just important to remember the direction's changed. Yeah. I know we had a similar question, I think, in the last one that we did earlier this week. Yeah. Yeah.
This is another thing. I probably could have just the residue is this, but I kind of did like a full kind of proof for it, and I went through and like did estimation lemma and things, and I probably didn't need to. And I was thinking, oh, this is quite a long question for 6 marks. You know, actually, if it's 6 marks, you can probably just do residue. You know, and it'll be fine.
Yeah, I mean, all I've just if you want to look at my full answer was literally. Was using this because it's holomorphic.
Yeah.
Blah, blah, everything like Cauchy formula. And then just said the arc, I've argued, looks like order 1 over r squared. Because we assume there's certain behaviour about f, right? That's what that bit was important for.
Yeah.
That allows you to get the 1 over r squared. And then just said therefore this bit is equal to minus a half residue.
Yeah.
That's all I said. And then just rearranged it to get exactly.
I think I need to, because when I do my problem sheets and things, I'm very I tend to write out each step and be quite particular about it, but doesn't quite work for the exams because you've got to get the thing done in 40 minutes.
Yeah.
I need to just change the way I write a little bit so I can get the point across without having to give all of the detail, you know. But we'll keep trying. I've still got 2 weeks to say.
Yes. Okay, last one. Formal maps. Okay, extending complex plane, add in infinity.
Yeah.
Stereographic projection, attempt to draw a punctured beach ball. How I think about it. Right, sort of, it's the point that you come through and then it's mapped down to. The point of the plane is the bit that you draw a straight line to the North Pole. That's the bit that punches the beach ball.
Yeah.
Right, brilliant. That was it. 3 marks.
Don't write that on the exam.
You could write punctured beach ball. That's okay. Okay, right. The fun part is part B, and the more standard part.
Yeah.
So, conformal map.
A conformal map is one that preserves angles.
Yes, but what's the easiest way to write it down? The
The
easiest way we think about it.
way that I did it was if you have 2 lines.
So you can definitely go down that route.
Okay.
We talked about this earlier this week.
It's conformal at z0 if f dash of z0 does not equal 0.
It's literally just f dash is non-zero. That's all they're looking for.
Cool.
It's good that you know how to do this.
Yeah,
It's literally we are just going to say it's conformal if f dash of z0. F dash of z is non-zero.
Okay, yeah.
F dash of z is non-zero in D, where f is mapping from D to C, and is also an f is holomorphic.
Yes, I'm all good with that. Yeah.
That's it. That means conformal. Because this is what the question was kind of hinting at various points, because we start with that and now it says show the Möbius transformations are conformal, compute the derivative, show it's non-zero unless it says except possibly at one point, so you compute, so obviously you're just saying f of z is the general Möbius map, we're going to differentiate it, compute f prime of z, which turns into AD minus BC over CZ plus D squared. And then you just say, oh look, that's non-zero, unless, potentially. Well, there's something weird's happening at Z equals minus D over C. So, problem point is that one. Problem point Z equals minus D over C. Right, so we want to exploit that one. And that was it. So you have to say, find a conformal map from the half strip to the upper half plane. Okay, I'm going to do this on a whole new page because I love these questions. Neither of you didn't do fluids, did you, Will?
Sorry.
No, it's fine. I'm just saying, if you'd done fluids, you would also love this stuff. half strip is this one, isn't it?
Yeah.
Right. Right. And that's at pi. And we want to end up in the upper half plane. Okay. So you have first done e to the iz. Why did you think to do that? That's what I did, but
I guess this is like I was thinking, okay, so your real part is between 0 and pi.
Yeah.
And your imaginary part is greater than 0. So kind of like between 0 and pi, you might think of maybe it's an argument, you know.
Yeah. No, good.
Yeah.
That's literally it. And again, we saw something similar on the last paper that we did earlier this week. Cool. You're just looking at this and saying, well, I want this to be an argument. Right? There's a reason. They just literally there's huge clues. If you've got something between 0 and pi or pi by 2, it's like, okay, this is going to be the argument, right? Whatever strip it is. So you need to have some kind of map where x becomes the argument. And then with a little bit of thought, you can hopefully realize that what you actually want to do is go from z to e to the iz. Because when you sub in, that's e to the ix minus y.
Yeah.
So we can see now the argument is fully determined by 0 to pi. So it's going to be upper half. However, the modulus is e to the minus y from 0 to infinity. So what's the limits on modulus?
So less than 1.
1.
Yes. So you're actually going to get the half of the unit disk. Right. So we're like that.
Yeah.
All good. And we also have 2 right angles, and we got 2 right angles, which is always nice.
Oh yes, conformal. Yeah, fine.
Yeah. Okay, what do we do to turn a half disk into, where are we trying to go? Upper half plane.
I think there are a couple of ways you could do it. The one which I went with was to just square it so you get a circle, and then I used a Mobius transformation to get to upper half plane. And maybe
I like that. I did it a different way, but I actually think that's possibly a little bit.
The other way you could do is use Mobius transformation to get this kind of. Maybe not actually. Could you make this into like the lower half plane and then kind of flip it, or maybe that's better.
So I turned it into a quarter plane and then squared afterwards. I think your way actually makes more sense, to be honest, because if you're going to square it, then that just multiplies your argument by 2.
Yeah, cool.
And of course it doesn't, because your modulus is between 0 and 1, squared it, still between 0 and 1.
Yeah. Fine.
So no, I think that's actually a better way to think about the map. Square here to get the whole disk.
Yeah.
And then we're all happy. And then the classic is we want the upper half plane. So it's going to be a Mobius map, but there's an even easier way to think about it, which is to be like, I want the upper half plane. So if I have a point here and a point here, this point is I and this is minus I.
Mm-hmm.
What inequality is true about the distance from z to I and z to minus I in the upper half plane?
Oh, you're closer to I than minus I.
You're always closer to I than minus I.
Yeah.
So you're like, okay, so looking at this, I can say the distance to I is always less than the distance to minus I, but that's the same as z minus I over z plus I is less than 1.
Mm-hmm.
So that's your Mobius map, because that's modulus less than 1.
Yeah.
So your Mobius map is z minus I over z plus I.
Yeah, fair enough. I mean,
would
that's
be
clever actually. It's probably saved me like a couple of minutes.
Yes. And obviously you can do it with left and right half planes.
Yeah.
Z minus 1, Z plus 1.
Yeah.
Same thing.
So anytime you're going between a circle and
On a half plane.
Yeah. Cool.
Just think about it like that.
Yeah.
Which point's closer? It blew my mind the first time I learned about it as a student, because I was like, I know how to do this as a Mobius map, but instead of having to compute where do I send 0, where do I send 1, where do I send infinity, you're just like, this is true, and it has the form of a Mobius map.
Yeah, nice.
So it's a really nice little trick at the end. Yeah, and then we just put them all together.
Yeah.
Last part. This is nice if you've thought about what we did in part 2.
Part 2 says, show that Mobius transformation is conformal at C except possibly at one point. I mean,
Where did we start? Here, right?
Yeah.
So how many corners have we got?
2.
Right, so there's 2 corners. How many corners have we got?
None.
Yes. Well, yeah. No.
Yeah. So we've changed from 2 corners to 0 corners. So a Mobius map allows you to change from 1 corner to 0 corners.
Okay.
Because you put the corner at the minus d over c point.
Yeah.
The one point that the Mobius map isn't conformal at.
At infinity. Yeah.
Yeah. You put that one in. But here, so that's literally it. You're just like, there's 2 right angled corners.
Yeah.
This one has none of them. A Mobius map is conformal everywhere except at 1 point.
Yeah.
That's why they asked you to show it wasn't.
I wasn't thinking about that.
So it was the fact that there's 2, so it can't work.
I ended up writing something crazy about, like, doing.
You can write about circ lines. You can also write about circ lines as well, because I did also write that down.
Oh yes, your method.
I
Yeah.
did it, yeah.
What did you say then, Luke?
I did it in a rush this afternoon, but basically I had a look and I found in this one, this point here, so 0, pi over 2 and pi, and infinity form a line.
Yep.
Whereas if you move it over into this one, for some reason my head thought it was a full strip, so my transformation was different. But I basically found you have like there, and infinity,
So no longer in a
which
line.
can't be
Yeah.
linear.
Right, yeah.
Don't know if that's still true with this transformation, but
So I also wrote here, bounded by 2 has 2 right angles, bounded by 3 lines. Mobius maps circ lines to circ lines, so you can't get a half plane because it's got to map the 3 lines to 3 other lines.
So you want to map this line, this line, and this line to 3 other circ lines.
Yes.
Right.
Which you can't do here because you can't map this 2 different ones to the same.
Of course,
Right.
yes, yeah.
Under a Mobius map,
Yeah,
you can't take 2 lines to the same thing.
Yeah, no, of course.
So obviously one of them goes to infinity.
Yeah.
One of your intersection points goes to infinity, but it's not going to work.
That's cool. I think
But I think the 2 points, that
Yeah.
to me is really nice, and it's what was being hinted at by this being like, there's only one.
Yeah. The takeaway is to look at the angles and say, okay, yes, where do the angles go? Oh, yeah, fine. Cool.
Okay, so I think that brings us to the end of the tutorial. So thank you again, Will and Luke, for allowing everybody to view your tutorial. That was very brave of you, so we all appreciate it, myself included. I'm sure everyone watching also appreciated that little insight into Oxford. And of course, thank you to all of you for watching. As always, if you've enjoyed this, please do subscribe to the channel. It's really helpful. And I'll see you all very soon in another video. Take care.